Okay, so we now consider a complex function, which is continuous on the image of a path. So here, okay. Okay, so we have so the image actually is a subset of the complex plane. C, okay, and f of z is continuous. This path means that it's continuous at every point on the image are gamma star. Okay, star. Okay, now so now this alpha beta is a bounded and closed. All right, so it's a bounded closed subset. Okay, so it is a bounded closed subset of R, right? And R is one-dimensional Euclidean space. So that means that this finite closed interval is a compact set. Okay, so it's a compact set in R, right? And a path, right? So a path is a curve, right? And a curve is a continuous function. So this is gamma is a continuous function. All right, it's a continuous function. So its image by our theorem we mentioned last week. So gamma star. So this means that gamma star is the gamma AB. Okay, so it's a continuous image. All right. So this is a compact. Okay, so it's a compact set. Okay, in C. Okay, it's a compact set in C. And as a compact set in C, so that so this implies that gamma star is bounded, at least bounded. Okay, and the closed set in C. Okay, so this is if condition, right? Right. So in Euclidean space, so as a geometric structure, we know a complex plane has the same geometrical structure as the two-dimensional Euclidean space. Okay, and we know a complex set is actually a bounded and closed subset. Okay, so we know gamma star is a bounded set. Okay. And also a compact set. Now, okay, and after okay, so we'll go this way. I'm sorry. Now, with the complex function, It's a complex function. Okay, it is possible that. So now, okay. So this is the F gamma star. Again, the gamma star. And because F is a continuous function. Okay, so this is continuous. Again, continuous function. So now this one is a compact. Again, compact set in C. Okay. Because gamma star is a compact set. So as a continuous image, because F is function, so it's a compact set in C. So that says that F gamma star is a bounded closed set in C. Okay. Any questions? Okay. So compactness, that's a very good geometrical property of a subset in Euclidean space, because the continuous image of a compact set is also a compact set. All right, so continuous function will carry on the compactness. All right, over. Okay, so that is an essential feature of compactness. All right, so now since, all right, since F of gamma star is a compact set, in C, okay, it is bounded. So that there exists an m greater than E0 such that f of z is less than or equal to m for all z in the gamma star. Okay? Any questions at this point? If no question, so then now we look at the absolute value of this path integral, the least line integral here. Okay, so the f of maybe I write here. Okay, and so by definition we know this is f of gamma t and gamma prime t dt here. Okay. All right. So you had an upper bound. If we take the absolute value in the integrand, so this is here, and the gamma prime t dt. Okay, so this is the upper bound here. All right, and because of here, for every point C in gamma star, the absolute value of the function value is less than or equal to capital M. So we have M here. Okay, yeah. And this is ML. Okay, where L is integral is the arc length of the image gamma star of the path gamma. Okay, so this is just the arc length. Okay, because gamma prime can be think as the velocity. Okay, so the absolute value is the speed and multiplied with time. So speed with time is the distance. So this is the differential distance, right? The distance along the path, and so we integrate over all time, traveling it through the path. This gives us the arc length. Okay, so L is the arc length. Okay. And the above inequality, okay, will be called the ML inequality. Okay, so when we refer to ML inequality of a line integral, we know that L is the arc length of the path, and the M is an upper bound, okay, of the complex function value over all points in the path. Okay. Any questions? Okay. All right. So now we will discuss Cauchy's integral theorem. Okay. First of all, I will mention a basic theorem. So suppose that f is an analytic function okay, on an open set omega. All right, and the gamma is a closed path in omega. Okay, so omega okay, so this is omega. It's an open set in a complex plane, and gamma, okay, is a path in omega. So gamma may be okay, right? So its image is contained in omega. Okay. And its image is here. Okay. Now, if the derivative, because we know f is analytical, so which means that this complex function is differentiable, right? On the open set. And the derivative, if the derivative f prime is continuous, okay, so if f prime is continuous on omega, then the line integral it's 0. Okay. So whenever the path is closed, then the line integral over such a closed path will be denoted by this. So we put a circle, okay, at the center of this integral sign to indicate that gamma is a closed path. Okay. Okay. So this line integral is 0. Okay. And the integrand is the derivative of f. Okay. And because we assume f is continuous, so of course this line integral is well defined. Okay, this is well defined. All right. All right. So let's see how to prove it. Now, by chain rule, all right, so we have, because f is analytical, so f is differentiable. And so if we take the derivative with respect to t, okay, so by the chain rule, this is, okay, so this is my chain rule. I have that. All right, and so let alpha beta, okay, be the parameter interval okay, of the path gamma. Then we look at the integral. Okay, so this is AB, and now by taking the change of parameters, so we have so this is f prime gamma t gamma prime, okay, and dt by definition, right? So you see, this is by substitution, right? Because we are integral over the path gamma, so we have that. But as we know that from this chain rule, so this is actually d dt and the f of gamma t and dt. Okay, this is the integral. And here this is a function of t, right? So that we have so by the fundamental theorem of calculus, so this is actually gamma b minus f gamma alpha beta alpha. Okay, so the difference. Okay, so I think this is the second fundamental theorem of calculus, right? And now this is 0. Why? Because gamma is a closed path, so the two endpoints are equal, right? Okay, we have that. Okay. All right, so the proof is easy. Okay. Any questions? Okay, so here is the fundamental theorem. calculus. Okay. All right, so we may take an example. So maybe we can make a remark to see. So for any point, right, A in C, and for any integer n which is not equal to -1, right? So we consider that. Then z minus a to the nth power is the derivative. Is the derivative of z minus a n plus 1 divided by n plus 1. Okay. So n cannot be -1. Why? Because if n equal to -1, the denominator is 0. It is not defined. Okay. So for any n not equal to -1, we know this polynomial is just a derivative of such a polynomial. Okay, such a polynomial. Okay, and this is true for all z. So this is true for all z in C if n greater than or equal to 0, and for all z in C but A if n less than or equal to -2. Okay? Because if n is less than or -2, then we know that because now the exponent is negative. Okay, and so if z equal to a, you have 0, all right, and with negative power, which is undefined. All right. Okay. Okay, so this is, and so now we consider gamma, so that so let gamma be a closed path in C if n greater than or equal to 0. And in C, but excluding the point, if n less than or equal to -2, right? Then we look at the line integral, the nth power dz. Okay. Now we look at this one. Okay. And we can apply the theorem here. Because in that case, when n is greater than or equal to 0, this is the polynomial. So of course, this derivative is a continuous function. Okay, on the image of every cross path. And also, if n is less than or equal to -2, okay, so we have a rational function, okay, and the denominator is a polynomial. So, and if so this function, so this derivative will be continuous for any path in here, because that a will not be in the image of the path. Okay, right. So this is 0. So this is a very interesting result, right? So that it depends on n. If n is greater than or equal to 0, right? Then this line integral is closed over any cross path in the compass plane. But if n is less than or equal to -2, okay, then this line integral is 0 for any cross path, right, which will not go through the point A. Okay, so A cannot be in the image of this path if n is less than or equal to -2. Okay, and also if n equal to -1, then this is not true. Okay, this is not true, and we will see if n is equal to -1. We have actually then a value which is not equal to 0, and we know what is that. Okay, but we will talk about that later. Okay. Okay. So you see, n is equal to -1 is a very special case. Okay, and it plays an important role. Okay, in complex analysis. Any questions? Go to here. All right. So now I will mention some the Cauchy's integral theorem. So we next present a couple of local Cauchy's integral theorem. Okay, right. So theorem 14.2.b. This theorem will be called Cauchy's integral theorem for a triangle. Okay. Now, omega, an open state in C, and P, a point in the open set omega. Okay, and F continuous. All right, so X is continuous in omega, and is continuous on omega, and is in the set of all analytical functions defined on this set. Now, omega is an open set, and P is a point in omega. So omega minus P is an open set in C. Okay, so you see that an open set. This is omega, which is an open set. But when you pick up a point inside P, this is the point P here. Okay. Now, so geometrically, for any point other than P here, you can find, right? You can find a neighborhood, right? So this neighborhood is still in omega. Okay. So which shows that omega and without delete the P, right? So this set is also an open set. Okay. All right. So our condition is that this complex function f is continuous on the whole open set omega, but we require only that this complex function is analytic, right? It's analytic at every point in omega except P. Okay, so this is the meaning. Okay, so f is in here means that f is analytic at every point in the open set omega except P. Okay, because sometimes we were faced with such a situation. Okay, we were faced such a situation. Okay, and now if a triangle is a closed triangle, okay, in the open set, then, right, so omega is a triangle in the open set. So now the triangle is here. So a triangle. So this is a triangle, okay, in omega, or another triangle. Right. So the triangle may contain P or may not contain P, but the triangle should be contained in omega, okay, and its cross means that this cross triangle will include its boundaries, means that it's 3 sides. Okay. So if delta is a closed triangle in the omega, then the boundary of the cross triangle. So the boundary of the cross triangle, you see, is a closed path, right? Because it consists of 3 sides. Okay, so this one delta is a closed path. Okay, so it's a closed path in omega, right? Right. So the 3 sides together is a closed path. All right, and so this line integral, right, and the integrand is f itself, and because f is continuous, so this line integral is well defined. And the conclusion of the theorem is that this is equal to 0. Okay, this is equal to 0. All right, so the situation is here. Omega is an open set. Okay, and f is a function which is continuous on the whole open set, and it is analytical at every point in the open set omega except the point P. Right? P. So P is some point in the open set. Okay, so this is the situation. Now, if we take a triangle, which is a cross triangle, and this cross triangle is contained in the open set omega. In this case, then the line integral of the complex function f over the boundary of the cross triangle. So the boundary actually is a cross path, right? Will become to be 0. Okay. So the statement of the theorem is here. Okay. So the important thing is that this line integral is 0. Right? And the proof is long, so I have write a proof for you. So please see the lecture note. Okay. Right. Okay, so this is the first local theorem. Now I'll present a second one. Right, so it's the Cauchy's integral theorem. Right, in convex, right, open set. Okay. So now omega is a convex open set in C. Right. A convex open set is that a convex set, as we know. So here, so I'll make a remark here. So a subset S in C is called convex if for any A, for any Z1, Z2 in S. Okay, the interval, the line segment. So join Z1 and the Z2 is in S. Okay, so you see, for example, a disk, right, is convex. The reason is that if we pick up a point here, okay, point here, then the line segment, join them, is still in S. Okay, so this set is convex. Okay. Now how about this? Okay, so this one is non-convex. Why? If you pick up 2 points here, now the line segment, right, joining Z1 and Z2 is not in S, right? It's not in X because that part of this line segment is out of X. Okay, so this set is non-convex. Non-convex. Okay, and okay, so the convex convexness is defined this way. So when you pick up any 2 points in the set, then the line segment join these 2 points should be in the set. If this set is called convex. Okay. Okay, so we can see the omega, which is convex open set. So it's open set and also convex. So something like that. For example, a disk, right? Particularly an open disk. An open disk is a convex open set. Okay. and P a point in omega. Okay. And the F is continuous, okay, on the whole open state, and is in, okay, so that so you may have a P here, okay, and omega. Okay. So this complex open state, right? And we have a complex function, which is continuous on the whole open state, and is analytic in every point in this open state omega, except a point P in the omega. Okay. Right. Then there exists an F, okay, in H of omega. Okay. Right. So there exists a complex function F, right, which is analytical on the whole complex open state omega, so such that F is just the derivative of F, right? And the line integral, right, is 0 for every closed path gamma in omega. So now you look at the difference between these two local Cauchy's integral theorem. In here, that omega is an arbitrary open set, not necessarily convex, arbitrary open set, okay? Arbitrary open set, and P is a point. And the complex function F is continuous on omega, okay? And also analytical at every point in omega except a point P here. And then this line integral can be 0 only for what? For the cross path is the boundary of a cross triangle in the omega. Okay, so that in this line integral, the path considered is restricted, right? Which is just the boundary of a crossed triangle, right, in the omega. Okay, so the whole triangle should be in omega here. Okay, just like here. All right, so you cannot consider the bound. So another case. Consider this open state. Okay, consider this open state, and P is here, right? And the triangle should be here or there. Okay. Right, but you can't consider triangle like this one. You can't consider triangle like that. Even though the three sides, the boundary is in omega, right? But the triangle itself is not contained in omega because there is a hole here. Okay. So this triangle cannot be considered. Okay. So that the cross triangle is the whole quadrant is to be in omega. Okay. So you can't consider such a triangle, right? You can't. Okay. So this is not true. Okay. This is not true here. But all other triangles in omega, this is true. Okay. So this local quantity theorem is for triangles, and the open set can be arbitrary. Okay. Here, the cross path gamma can be arbitrary, not necessarily the boundary of a cross triangle, not necessary. Okay, that it can be anything, but we require the open set to be convex. Okay, so we restrict a subclass open set, which should be convex open set. Okay, and in this case, that the cross path gamma, the gamma can be arbitrary cross path. Okay, can be arbitrary cross path here. So the path you may use something like here. You like all right. So this weird cross path, right? So over this weird cross path, okay, that the line integral is 0. Okay, and the f can be just continuous on omega, and analytical at every point in omega except a point p. Okay, right. And also, in addition to this nice result, actually we have that there exists a complex function, capital F, which is analytic, okay, which is differentiable at every point in omega, such that the little f, the original complex function f, is just the derivative of f prime. Okay. So this is our result. Okay. And to prove the theorem here, we use the Cauchy's integral theorem for triangles. Okay, for triangles for here. And so proof. So please see the lecture notes. Right? And the theorem 14.2.b is used. Okay. So that is the, and any questions? Right. So now I stop here.